This is NanoSpark speaking, igniting sustainable power through nano devices. Our group is led by Professor Jian Chen with three students, Yizhen Huang, Yiting Li, Shixiu Chen. Today, our study is about wearable thermoelectric innovation for sustainable remote health care. This video is going to be divided into four parts: abstract, strategy and prototype, result and practical assessment, and finally the conclusion. Nowadays, the proportion of elderly people in the population is increasing year by year. The world gradually transforms into an aging society, and the issue of elderly care has become a growing concern. Over the past 2 decades, technology has grown explosively in the past 20 years. With the rise of artificial intelligence and big data, things that seemed impossible 20 years ago are now becoming a reality. In the past, elderly people in need of proper medical care often required a full-time caregiver or had to stay in hospitals for constant monitoring. Today, thanks to wearable devices and the smart medical devices, we can instantly track data and send it to medical professionals. This approach can achieve the effect of remote medical care services. In an aging society, this kind of technology is no longer just a convenience, it's a necessity. As a result, the market for remote healthcare is expanding rapidly. In fact, it's expected to exceed $400 billion by 2026, with a remarkable compound annual growth rate of 33.2%. In response to the growing demand for remote healthcare, wearable devices have become essential. Today, there are already many personal devices capable of monitoring various health indicators. For example, even the popular Apple Watch includes a built-in app called Health. However, true medical-grade care requires more stable and accurate sensors to continuously track health data. When combined with artificial intelligence and big data analytics, healthcare professionals can provide comprehensive, real-time support and even predict and prevent emergencies before they happen. But to keep these systems running reliably, there is a crucial factor we must consider: power. Stable, self-sustaining energy sources are key to making wearable devices more practical in the long run. To address this target, we developed a wearable thermoelectric device using a composite material made from the organic polymer P.PSS and carbon nanotubes. This device can effectively convert body heat into stable electrical energy at room temperature. By eliminating the need for frequent charging or battery replacements, this innovation significantly improves reliability and user convenience. It also aligns with the global goals for sustainable development Goal 3, good health and well-being, and Goal 7, affordable and clean energy, by transforming waste body heat into clean energy that powers personal healthcare equipment. Now, let's explain the strategy behind our material selection. We chose the organic conductive polymer P.PSS as our base material. It is non-toxic, environmentally friendly, and can be easily processed using solution-based methods, making it the ideal choice for wearable applications. Building on P.PSS, we incorporated low-cost multi-walled carbon nanotubes to form a composite material, which significantly enhances the electrical conductivity. To further improve the thermoelectric performance, we applied a simple post-treatment by using DMSO, a polar solvent, along with sodium borohydride, a simple reducing agent. Our results show that under a specific concentration of sodium borohydride, the oxidation state of P. can be moderately reduced, while still maintaining a strong heterojunction interface between P. and multi-walled carbon nanotubes. It is important because it preserves the material's ability to perform energy filtering, a key mechanism that boosts the Seebeck coefficient. Now, what is the Seebeck coefficient? It's a fundamental parameter in thermoelectric materials, and it's the core principle behind our device, the Seebeck effect. It essentially determines how efficiently a material can convert heat into electricity. Through the combination strategy of improved charge transport and enhanced energy filtering, our composite material achieves a significant boost in thermoelectric performance, paving the way for stable, self-powered wearable health devices. After preparing our composite material, we used solution processing and spin coating techniques to fabricate thin films. These films were then formed into essential components of the device, which we called thermoelectric legs. By connecting these legs in series with conductive wiring, we were able to increase the overall output voltage. The entire system was built on a flexible PET substrate and soft multicoil wires, forming a wearable thermoelectric patch that can generate electricity using the heat from human skin. Thanks to the use of flexible materials, our device can comfortably conform to various parts of the human body, achieving reliable body heat part self-generation. What's especially noteworthy is that our film fabrication method and its application have been granted multiple patents, including both Taiwanese and US patents, which significantly enhances the credibility and potential impact of our research. Next, let's take a look at the thermoelectric performance of our P.PSS multi-walled carbon nanotube composite. By adjusting the concentration of the sodium borohydride reducing solution, we were able to precisely control the oxidation state of P dot, allowing us to optimize its thermoelectric properties. As shown in our results, when the soaking concentration of sodium borohydride reached 20 mmol, the material achieved its highest Seebeck coefficient of 226.2 microvolts per Kelvin. Additionally, from the IV characteristics of a single thin film, we calculated the maximum output power to be 233.9 nanowatts, the highest among all tested conditions. These results clearly demonstrate the potential of our composite material as a key component in practical thermoelectric devices. To test the effect of our device, we used common heat sources from daily life, including the human fingertip, warm water at around 40 to 50 degrees Celsius, and even a higher temperature copper block heated to about 150 degrees Celsius. As expected, when we applied a heat source to one side of the device, we observed a clear output voltage. More importantly, the output voltage increased proportionally with the temperature of the heat source. The hotter the source, the greater the voltage generated. These results confirm that our wearable thermoelectric patch can effectively convert body or environmental heat into usable electricity, and it responds well even to low-grade heat sources like human skin. We also demonstrated non-contact heating using a hairdryer, which provided an air temperature of approximately 60 degrees Celsius. The device was connected to an Arduino module with an LED light in series. LED light will emit when it receives a voltage difference. As shown in the video, when the device detected a temperature gradient even from a distance, it successfully generated voltage, causing the LED to light up. This clearly illustrates our device's sensitivity and responsiveness to heat, even when the source is not in direct contact. It highlights the practical potential of our thermoelectric patch in real-world low-grade heat occasions. Finally, we integrated our device with a cooling hydrogel patch to create a structure capable of generating a temperature gradient on a single flat surface. This is a key design feature for wearable applications. We attached the device to the wrist, using body heat as the heat source and the hydrogel as the cooling element. Under these conditions, we measured an output voltage of approximately 19.7 mV. This voltage is sufficient to power other sensors in series or to drive low-voltage medical components, enabling self-powered operation in a wearable format. These results clearly demonstrate the potential of our device as a power source for wearable medical electronics, offering a sustainable and practical energy solution that responds to the human body. In summary, by using a P.PSS multi-walled carbon nanotube nanocomposite strategy and applying a two-step solution-based post-treatment, we were able to significantly enhance the thermoelectric properties of our thin films. The result is an efficient and stable device that can convert body heat into electrical energy at room temperature. This design is not only low-cost and effective, but also highly practical for long-term monitoring applications. Our work offers a new strategy for energy harvesting, one that holds strong potential for self-powered systems and wearable healthcare technologies, bringing sustainable energy solutions closer to everyday medical care.